All right, everybody. Last example for this chapter. So once again, we're going to put it all together. Determine the equation of any asymptotes of f of x is equal to 2x squared minus 5x plus 5, all divided by x minus 2, and use this information along with the intervals of increase and decrease and local maxima and minima to sketch out what the curve looks like. So to start with, if f of x is equal to 2x squared minus 5x plus 5 all over x minus 2, then I can see that from this and the denominator, x cannot equal 2 for this rational function. So right away, I have a vertical asymptote at x is equal to 2. I'm going to divide it out because I can see that the degree of numerator is 1 more than the degree of denominator. And I'm going to use synthetic division in this case. And I can see that I could rewrite it as f of x is equal to 2x minus 1 plus 3 over x minus 2. Because as it approaches infinity, this would approach 0. I have a slant asymptote at y is equal to 2x minus 1. All right, there is our first piece. Step 2. Intervals of increase and decrease. If f of x is equal to 2x squared minus 5x plus 5, all divided by x minus 2, then f prime of x is equal to 4x minus 5 times x minus 2 minus 2x squared minus 5x plus 5 all times 1 divided by x minus 2 squared, just using that quotient rule. I'm going to simplify this. 4x squared minus 13x plus 10 minus 2x squared plus 5x minus 5 all over x minus 2 squared. And f prime of x is going to equal 2x squared minus 8x plus 5 all divided by x minus 2 squared. I'm going to use this information to find what the critical numbers are. If f prime of x is equal to 0, then 2x squared minus 8x plus 5 is equal to 0. Can't seem to factor this, so I'm going to say that x is equal to the negative of negative 8 plus or minus the square root of negative 8 squared minus 4 times 2 times 5, all divided by 2 times 2. Which means that x is going to equal 8 plus or minus square root of 24, all divided by 4, which means that x is equal to 2 plus or minus root 6 over 2. Now I can approximate this as 0.78 and 3.22, so I get a general idea of where it would exist on the graph. All right, let's carry that forward to our first derivative test for that increase and decrease, local maxima, local minima. So we have a vertical asymptote at x is equal to 2. We know that if we try to solve critical numbers from the denominator, we would get that 2, except for that is not part of our domain. We have that 0.78, and we have the 3.22 approximately for the 2 plus or minus root 6 over 2. And so I'm going to pick some test points. So I'm going to say that I have x is equal to 0, x is equal to 1, x is equal to 3, and x is equal to 5. And what I find is f prime of x is going to go from being positive to negative to negative to positive, which means that my function is going to go from increasing to decreasing to decreasing to increasing, where we can see that we have a local max here, we have a local min here, and we know in between them that is our vertical asymptote. When I'm solving my local max, then if I take f of approximately 0.78, I'm going to get what approximates to negative 1.89. When I take f of 3.22 to get my local min, that's going to approximate to 7.89. Well, this seems weird considering that my local max is smaller than my local min, but if we think about what is happening here, when I actually go to my step 8, my graphing, then I'm going to have a vertical asymptote at x equals 2. I'm going to have a slant asymptote at y is equal to 2x minus 1. I'm going to have a local max at (0.78) and negative 1.89. And I'm going to have a local min at 3.22 and 7.89. Here it is approaching the asymptote and increasing. Here it is approaching the asymptote and increasing. Here it is approaching the asymptote and decreasing. And here it is approaching the asymptote and decreasing. And there's my graph.